Bismillahirrahmanirrahim. Before starting this session, if you have any question or any comments from the previous section or overall the Z transform. Okay. Okay. Let me start the new section here with the okay. Here we were discussing on the IIR filter design, the fundamental filters. We are talking about the low pass filter and the high pass filter. We have already covered the low pass and the high pass filter. Just to mention it again, if we want to compare the FIR and IIR filter, FIR and IIR filter, we have already found that in this case, the FIR filter, the phase response is linear. That is a very important criteria of this kind of filter. And for the IIR filter, the phase response is non-linear. So from the practical experience with some online platform, we will give you some example based on the filter design, where we'll consider the IIR filter, and we'll see that how the phase is changes when we are considering the same kind of low pass and high pass filter for IIR type. Okay, so let me start the band pass filter, which is also IIR pattern. So from our previous experience, okay, we know that how to design the band pass filter for the FIR one. If you can recall, this is that part. In the numerator, we are taking the exactly same equation, where it shows that definitely the zero locations are on the unit circle, and one is at the -1 and one is at the +1. So that is known to us. And now here we have something in the denominators, which is exactly taken with some pole location. So first of all, let that this is the denominators we are just taking. So step by step, we will give you the idea how we can build this denominator part. So what I have mentioned here, the numerator part, you have this experience from the FIR filter, and this actually been taken from the location of the 0 points. In the denominators, definitely this is responsible for the pole location. So first of all, we are not selecting the pole location. We are just writing some arbitrary equation. Definitely that is a second order equation. So we are going to find two pole locations. Okay, so this is one kind of trial and error method. We are just taking some equation, and let me introduce what does this beta and this alpha mention here. Step by step, this is HZ. We let that, so we can remember this equation, but here you don't need to remember at this moment. Just try to understand the thing. From this equation, for the maximum value H omega, where you find H omega equals to 1. I haven't derived that things here. You can derive yourself, and that is your task. For the maximum value H omega equals to 1, you can find that the cos omega 0 is equals to beta. What is omega 0? Here, if we can go to the magnitude plot, here the central frequency that is known as omega 0. Of course, this omega 0 can be shifted in any direction, both to the higher value of omega or lower value of the omega. For this example, let's say this is omega, and whenever we are talking omega 1 and omega 2, those are the two cutoff frequency for the band pass filter. So if you consider this equation, the fundamental equation of this one, so here put it is equals to 1 and solve this equation, and for that equation you find that the value of cos omega 0 is equals to beta. From there you can find the cos omega 0 is equals to cos inverse beta. Again, for the fundamental equation, whenever we are taking this magnitude is equals to 1 divided by √2, that means you are targeting the cutoff frequency. In that case, you will find two values of the omega. Let's say you are getting two values. One is A and another one is B. So omega 1 is equals to A and omega 2 is equals to B. I'm just giving some arbitrary example where A is less than B. That means this omega 1 is the lower cutoff and omega 2 is the higher cutoff. Since this is a second order equation, the fundamental equation is a second order equation, you should get for this, when the amplitude is 1 divided by √2, that means you are targeting the cutoff frequency. And since from that magnitude plot, we can easily understand that for the value of 1 divided by √2, we'll get two values. And of course, whenever you got two values, omega 1 should be less than omega 2. And that is how you can define this is the lower cutoff and this is the higher cutoff. And whenever you found omega 1 and omega 2, then you can subtract omega 2 minus omega 1, which can be represented as the bandwidth B. And from that equation, you can find or you can derive this cos inverse 2 alpha over 1 plus alpha. Okay, so here these two terms are very important. Number 1 is this, and this is number 2. So in case of any bandpass filter, we have two terms significantly we want to control: the center frequency and the bandwidth. We want to control these two. And as you can find from these two equations, equation number 1 and equation number 2, by controlling the value of beta, you can control the center frequency. So that means you can change the value of beta and you can shift this omega 0. So you can control this omega 0 by changing the value of beta. On the other hand, if we talk about the bandwidth, how you can control the bandwidth by changing the value of alpha. So the bandwidth, the B, is directly or indirectly, whatever it is, it actually been controlled by the value of alpha. So if you want to fix the bandwidth and want to shift the omega 0, it can be possible. On the other hand, if you want to fix the omega 0, you want to remain here and want to squeeze the bandwidth or expand the bandwidth, you can also control it by the value of alpha. So that is the beauty. That is the beauty of the IIR type of filter. You have a lot of flexibility from the design part. Okay. So this part here, this part actually been shown the 0 locations, how to find the 0 locations. Okay, so we have already derived this previously. So I have taken this part from the numerators of the HZ, that means our filter. And from there, putting the value of 0, we can find that where are the 0 locations. I'm not going to details here. So you know that we'll find the 0 locations here. So those are the 0 locations for this kind of filter. And this is the magnitude response for particular cases. I have already mentioned these 2 facts. That means the beta determines the center frequency and the alpha determines the bandwidth, and they are independent. So independently you can do that. So the quality factor of the filter can be defined as center frequency over the bandwidth. Here you can find that the quality factor can be controlled by these 2 facts independently. So those are the advantage of the IIR type filter design. Now the question is, we need to find the pole locations. What are the pole locations? Definitely the pole locations are not fixed here, because it actually depends on the value of beta and value of alpha. So we can give this example of the pole locations based on one specific example. Let's say, given that omega 0 is equals to pi by 2. So that means you have the center frequency at pi by 2. So if we draw the frequency spectrum, the magnitude response plot. So we have 0 here and we have pi there. And if this is a pi by 2 and this is your omega 0, that means this is a center frequency. Center frequency shows that it should have the maximum value, maximum amplitude, 1. Okay, so from there you can definitely find that, okay, it might be looks like this. But again, you can't say that what is the bandwidth. The bandwidth can be controlled by choosing the value of the alpha and the beta. For a case, it might be looks like this. That means you are squeezing the bandwidth. You might squeeze more of that by changing what? By changing the value of alpha, because as you know that the bandwidth is depends on the value of the alpha. So by controlling the value of alpha, you can control the bandwidth. What about the center frequency? The center frequency omega 0 can be controlled by the value of beta. Since omega 0 is now fixed, so we don't have anything to do with the beta value, because that represents a single number. Okay, so you can find it here. So omega 0 is given, and the bandwidth is also given here. The bandwidth is pi by 4 is also given. Now the value of Q is this one. So Q is equals to omega 0 divided by B. So we have 2. So now from there, we can find the value of alpha and also value of beta. So what is the value of alpha and the beta? Okay, so as we already know that the omega 0 is equals to cos inverse beta. So the beta is equals to cos omega 0, and omega 0 is equals to pi by 2. So we can understand this is equals to 0. So beta is equals to 0 for this case, for this particular example. So in the example, it has been given that omega 0 equals to this and B equals to this. Those 2 informations are given. Now our task is to find the value of pole locations and the 0 location. So what about the 0 locations? It will remain the same, because there is no dependency from the alpha value or the beta value. So the zeros remains the same. Now the question is, where is the pole locations? Okay, so first of all, we found the value of beta. now we need to find the value of alpha. We have another equation cos b, where b is the bandwidth. So cos b is equals to twice alpha over 1 plus alpha square. We have already derived this. And now cos pi by 4 is equals to twice alpha divided by 1 plus alpha square. And as we know that it is equals to 1 by root 2. Why? Because that is the cutoff value. It actually gives the cutoff value. At this, we have the amplitude is equals to 1 by, or sorry, that is not the cutoff. In a sense, that makes a cutoff for the omega 1 and omega 2. However, in this case, that is not the fact. So we have cos pi by 4, and that is equals to 1 by root 2. So from this equation, we can find alpha is equals to, since this is a second order equation, we can find that alpha is equals to root 2 plus minus 1. So now the question is, we have two values, root 2 plus minus 1, and which one we can take for finding the pole. This is only the alpha. This is not the pole location. Try to understand that we have two factors. One is beta and another one is alpha. Based on these two values, you can find the pole location. So you have already find the value of beta, and that is equals to 0. And now you have found the value of alpha, but unfortunately there are two values. So now we need to select which value we should take to find the pole location. To find the pole location, definitely you can, if you can recall the fundamental equation of the filter, we can find that this is our denominators, and which is a second order equation. So from this you can find two values of z. There would be two values of the z, and which actually gives you the essence of the pole location. So here, nothing very special. Since that is a second order equation, you can go for this kind of the root finding equations, and from there, okay, we'll find this equation. So now by putting the value of alpha and the beta, you can find those pole locations. The interesting part is the beta is now 0, so it makes your life very easy. So putting the value beta equals to 0 and let alpha is equals to root 2 minus 1. So what are the values of alpha? One is root 2 minus 1, and another one is root 2 plus 1. So we have chosen at the first place, we have chosen root 2 minus 1 and put it to that fundamental equation. So you have hz, put the value of beta equals to 0 and the alpha equals to 0. You can put it to the fundamental equation, or what you can do, you can directly put it to this equation. If I put it directly to this equation, then what I have found, this part definitely goes to 0 because beta equals to 0. And this part is also goes to 0 because beta equals to 0. Then we can find only plus minus root over minus alpha, and which can be mentioned as plus minus j root over alpha. That is the value of z for this case. You can do it like this. So if we go to the main function, you can proceed, and afterwards whatever you have found, it is like this, the same thing what I have shown you earlier. So whenever you found this in the denominators, this denominator part should be is equals to 0 to find the pole location, and from there you can find this is the pole location what I have shown you earlier. So that means plus minus j root over alpha, where alpha is taken as root 2 by root 2 minus 1. If you think about closely, on this term, you will find that this term is always less than 1, because root 2 is 1.14 or something like that, so a little bit higher than 1. Minus 1 gives you a value which is less than 1, and root over that is definitely less than 1. And of course the pole location should be less than 1 for the stability. If you have the pole outside the unit circle, so this is the unit circle, these are the zeros. Where are the poles now? They are in the imaginary. This J means they are in the imaginary plane. So the pole should be here and the pole should be there, because they are complex conjugate. One is plus, this one is plus J, let's say root over 2 minus 1, and this one is minus J root over 2 minus 1. The magnitudes are taken, these magnitudes actually been taken from the value root over 2 minus 1 root over that, and plus and minus actually been plus J and minus J, show that in which axis it will, so the rotation of that part. So from our understanding, since this is inside the unit circle, so we can take it. So it will give us the idea that if we took alpha is equals to root over 2 minus 1, that is good. That is okay, or that is acceptable. That is acceptable. So you can accept this value alpha is equal to root over 2 minus 1. On the other hand, if Z is equals to plus minus J, if I took alpha is equals to root over 2 plus 1, what happens? We have root over plus 1, and that makes the pole outside the unit circle, which is not acceptable. So this term is plus J root over 2 plus 1, and this term is minus J root over plus 1. So that is not acceptable. So in this way, we can find the pole locations and the zero location of the system, and it looks like this. Okay, so this is our band pass filter. Okay, at this moment, let me move on to the next section. The band stop filter. Now to the band stop filter, it is exactly, we are taking the equation exactly like the same, just changing the value. So if I go back to the previous section, that means the band stop filter, the actual equation. Okay, this is the actual equation. We have exactly the same thing, but here what we have done, definitely we need to put a plus, because that makes sense, and that actually gives you the zero location on this. So which shows that you have the 0 at pi by 2. So you have the 0 at the location of pi by 2. You are putting the 0 at, because the 0, we are putting 0 at omega equals to pi by 2. It shows that you must have a 0 over pi by 2. But if you fixed it over there, then you can't control this frequency. You can't control this frequency. Just to control that frequency, what we have done, we are putting a variables here. Okay, so we are putting a variable. So what I am mentioning, if I put 1 plus z to the power minus 2, what happens? You are not controlling the pole, the zero locations, and that makes a problem that your notch frequency can't be controlled. However, by putting this term, extra term here, we can control the notch frequency. Okay, now we can control. So I have already discussed it with this green box. You can go through that and you will find it very simple. So do the mathematical calculation for different values. So whenever you need to find the value of omega 0, in that case, of course, what is the magnitude? The magnitude is 0. So if I have the equation, we have the equation. So the magnitude of this should be 0, and this is at omega is equals to omega 0. From this condition, you can find this equation. This equation, omega 0, cos omega 0 is equals to beta. And on the other hand, similarly, if we have hz, we have already defined that, and the magnitude of this is equals to 1 divided by root 2, similar to the previous one. You can find two values of the omega 1 and omega 2, and from there omega 2 minus omega 1, it gives the bandwidth, and you can establish this equation. Please do it yourself, and if you find any problem, then just let me know, we can discuss it in the class. So those are the two fundamental equations where they are independent. Again, beta will control the center frequency or notch frequency, and the alpha will control the bandwidth of the filter. So you can control the bandwidth of the filter. We'll see that with some practical example. So try to understand this alpha actually being given the essence of the pole locations, where the pole location should be. Okay. So for example, if it is given omega 0 equals to pi by 2 and the bandwidth, so like the previous one, so do the calculation and try to find the pole location. Try to find the pole location for this given example. So this is your task. Whenever you will return your class note for this lecture, so please do it and put it in the class note so that I can check whether it is okay or not. Okay, at this moment we can again introduce this platform to understand the example we have already given here. Okay, so first of all, let me design. Okay, of course this is okay, so I would like to cancel this out. So this one is the blank filter. So real zeros, we can put the real zeros. Take it like this. 1 0, 1 0, and another 0. We'll design the band pass filter for the IIR type. So where the pole locations, we already know that the pole locations, we need to put the complex conjugate poles, because we already know that, and we are putting those complex conjugate poles. Okay, before going to that, let me introduce the low pass filter first, IIR type low pass filter. So this is the IIR type low pass filter we can put here. Okay, to try to understand here with the magnitude response and the phase response. So if I just show the phase response here, and we have the magnitude response in the upper side. So if we change the pole locations, of course, you can find that, of course, the quality of the filter is improving. Here, when it is at the center, the quality of the filter is very low, poor, but it is, you can see the phase response is linear. So that is a FIR type filter. Whenever we are just putting the pole locations very close to the unit circle, you can find that the quality of the filter is improving. However, now you can find that this phase response is non-linear, and that makes a problem. Which kind of problems? Definitely we'll discuss. It makes a phase distortion. Whenever you have the signal, input signal, and you are filtering the signal, and you are get back to your original signal, then if there are some phase distortion, then you can't get back your original signal. There are some distortions. So we'll discuss that. So whenever we are putting this more to the unit circle, you can see that your phase response is more non-linear in properties, but the quality of the filter. So you need to make a trade-off between non-linear phase and the quality of the filter. Okay. And if we think about the high pass filter, okay, so that is the same thing. For the IIR filter, you'll find that FIR type filter, this is a linear, the phase is linear. And now if you want to improve the quality of the filter, you can find that the phase becomes non-linear in for different quality filter. Okay, now we can observe the bandpass filter. Bandpass filter. So this is the fundamental pole locations, zero locations. Now we are putting the pole locations, and that is a complex conjugate. Okay, this is a complex conjugate, and you can see that this phase, if I only think about the phase, this is again non-linear in pattern. And by changing the pole locations, what you can find, you can control the bandwidth of the filter. However, the non-linearity of the phase is improving or increasing whenever the quality of the filter will also increase. So that is a challenge for the designers. Okay. Now, how you can shift the omega 0? By omega 0 means the center frequency. Here the center frequency is at the center at the location of pi/2. Now you can change it like this. You can shift the center frequency, or you can shift the center frequency. So arbitrarily, you can improve the quality and the center frequency by only changing the pole location. And if you consider the time domain responses or time domain sequences, you can also find some changes in the time domain. Definitely, they are different filters. They are different in pattern. Okay. So you can play with this. This tool is very handy for understanding. Okay. Now for the stop band or notch stop band, for that one we can put conjugate pole location. So because we need a notch here, so that's why this is obvious. And what about the pole? You need to find that a pole location. However, I can just put something over there and try to understand where it can be, where it can makes it. So if you want to make it band stop, of course the pole locations are also in the imaginary plane, and you can find that now the phase response is non-linear in pattern. But what is the advantage? The advantage is now you can control the quality of the filter. So you can control the bandwidth of that filter here, and you can also control the bandwidth in that way, but that is not very reasonable. If you want to control the center frequency, definitely you need to change. So you can change the pole location. Okay, you can change the zero location, as well as you need to change the pole location to make it a realistic notch band filter. So you need to change both the pole locations and the zero locations for this purpose. However, you can change only the pole and the zero location. That will definitely change the notch frequency, where you are targeting your notch frequency. It definitely depends on the zero location. I believe you can understand now. So how they are operating in the magnitude response and the phase response. In several times, I'm telling that the phase response is very important for signal restoration. So whenever you need to restore the signal, you need the phase, the common phase, or you need to know about the phase properly. Okay. Okay. Moving to the next section. We can discuss on how to improve the quality of the filter. We have discussed a little bit before. In case of FIR filter, how to do that, and that is by cascading. And we have also mentioned that in case of low pass, high pass, and band pass filter, the cascading will work. However, for the band stop filter, that will reduce the quality of the filter. So we have already discussed it with a graphical example. In case of IIR filter, you can change the location of, or controlling the location of the mostly the pole location. By controlling the pole location, you can control the quality. You can improve the quality of the filter. Okay. Before going to this COM filter, there is another kind. Okay, let me talk about the COM filter first, and then if we have time, then we'll talk about the all pass filter. And before all pass filter, we need to know about why we need all pass filter. Okay, let's start with the COM filter. From the name of this filter, you can understand how it should looks like. It looks like a COM. Okay, and that's why it is actually known as the COM filter. Okay, so first of all, let me show the magnitude response of a COM filter. So this is a COM filter. It can be looks like this, or it can be looks like this. That means you can design some filter like this as well, the opposite in nature. Okay, whatever the case, it looks like a COM. What is the purpose to do that? First of all, the purpose of designing this sort of filter is to reject the 50 hertz and the harmonics of that. So as you know that in almost in all cases, we have the power line carrier frequency for Bangladesh, that is 50 hertz, for USA, that is 60 hertz. So the British ruled countries actually follow this 50 hertz, and the USA and alliance are following this 60 hertz. So whenever you are designing some instruments, then always we found that in the signal we have 50 hertz noise. They are incorporated from the power line carrier. So let's say this represents 50 hertz. So you need to delete, or you need to bypass that 50 hertz. So we need to design this kind of filter by choosing specific value of the pi. Similarly, we have 50 hertz noise. We also have the harmonics of that 100 and 150, something like that. So in that case, this COM filter is a very essential filter for targeting or rejecting 50 hertz, some basic filter, basic signal, as well as their harmonics. And also in many cases, it also been very effective for rejection of periodic interference distortion. So if there are some interference between two radio channel and their harmonics, then we can also use this kind of COM filter. So this is a sort of special type of filter you can design. Okay, so now from the mathematical perspective, how could we design a COM filter very effectively? So according to the design side, we have a filter HZ. We have already designed a filter HZ, which is a low pass filter, So how the low pass filter looks like? Of course, it looks like this. And now we want to make some COM filter based on this low pass filter. So in that case, the low pass filter, the COM filter GZ is equals to H Z to the power L, where L is an integer value. It can be any value L, let's say integer value 1, 2, 3, 4. So in general, okay, we are taking some value like 4 or 5 for our purpose. So we are starting with a low pass filter, and then we can convert. So this is okay, so don't be confused, this is exactly L. There is no minus here. Okay, this is L. So ZZ is equals to HZ to the power L. So what is that? It can be written as half 1 minus Z to the power minus L, because we know that the HZ is equals to half 1 plus Z to the power minus 1. Now this value, the Z, now the Z is replaced with the value of Z to the power L whole to the power minus 1. So it will given as this. Okay, so that is the filter. We have designed our COM filter. Now we can do the analysis, the magnitude response. So to do the magnitude response, always it's convenient to convert it to the Fourier. So in the frequency domain, so we can find it. This is equals to half 1 plus e to the power minus j omega into L. So you can take common over there, e to the power minus j omega L by 2, and then we have e to the power, so we are talking minus, so we have plus there, so plus j omega L divided by 2 plus e to the power minus j omega L divided by 2. So this is nothing but the cos. This is equals to twice cos. This is equals to twice cos omega L divided by 2. So you can replace that with this 2 and 2. They will cancel each other. So at the end, you can find this equation. So here, if you concentrate closely, what you can find, this is the phase. So you can find the phase is linear again. This is a linear phase filter because it is omega minus omega L by 2. That is, of course, a linear phase filter. What about the magnitude? It depends on this factor. This is cos omega L divided by 2. Now, if you want to find where is the 0 and where is the maximum. So where is the maximum? We can find the magnitude is equals to 1. From there, we can find this equation, and we can find this is the condition for getting the maximum, where R is the value from 0, 1, 2, 3 up to L minus 1, and L is an integer. And when you got the 0, you can find magnitude equals to 0, and from there you can find this condition as well, where k is the value 1, 3, 5, something like that. So now if you want to plot it by understanding these two condition, omega equals to twice pi r divided by L, and omega is equals to pi k divided by L. So we can draw this magnitude response. At which point we have the maximas? We have the maximas at the location when we are putting r equals to 0, we can find there is a maxima. Here we are putting L equals to 5, so we can replace L to the 5. When r is equals to 1, we have the second maxima, which is actually twice pi by 5. Where is the third maxima? This is, of course, r is equals to 2, that is 4 pi divided by 5. Similarly, where at the minimas, put k is equals to 1, so it will give you pi by 5, and of course it looks like a cos function because it's a cos function, and the other one will goes like this and like this, and so this is a cos function. Basically, this is a function and the inverse of that one. So this is the design how we can do it like that. If you want to design a filter like this, okay, concentrate on this point. It looks like a high pass. This part looks like a high pass. So we can start with the high pass, and then we can follow the same principle. So it can give you the filter like that. So that has been discussed here. If we start with the high pass, in that case, if you want to design that kind of filter, that means you want to take the high frequency and block the low frequency, and your DC value is the targeting frequency. You want to block the DC value. This point represents the DC value. If you want to block this, of course, this pattern, the green one, what I have designed already, this will not work. In that case, what you need to do, you need to design your filter in such a way that your DC part will be blocked. In that case, what kind of filter you need to start with? You can start with the high pass filter and follow the same process, and you can design the COM filter as prescribed. Okay, so that is the COM filter. Then the next section is the IIR all pass filter. This is a very important filter for communications and as well as for different purpose, mostly for the communication engineering. Okay, let me discuss about the nonlinearity of the phase. Okay, so there are two terms. Okay, before going to the all pass filter, we can discuss on, this is important, discuss on the group delay. These are the all pass filter, group delay, and the linear for the linear phase and for the non-linear phase, how we can say the group delay, and with some examples of the group delay. So first of all, what is the group delay? With some equation, first of all, I'd like to introduce with some equation, and afterwards we can find exact value of the group delay. For the linear phase, what we have, let's say the linear phase can be represented like this. Previously, we have this kind of thing, like omega minus omega, or let's say minus omega L by 2. So in that case, you can find, in this case, what is the value of ND? So it is like 1. For this, what would be the value of that? Let's say L is equals to 4. In that case, the group delay, the linear phase delay, the phase delay is minus omega into 2. So that means the ND here, we have a constant value. This value is represented by this term. So after omega, so what is the phase? What is the number? So this is the linear phase. And now if we differentiate that phase with respect to omega with a negative sign, that known as the group delay. For this example, we can find the group delay is equals to minus d by d omega into minus omega in nd. Okay, whether this is a small n or capital N, both are the same. Okay, that is a constant. We have the group delay is equals to this nd. Here, what is nd? This is the sample number or a constant number. So you need to make a delay of this number of samples to reconstruct your full signal. Okay, so we need to understand it properly. So all the signals or the frequency component have the same amount of the delay, and which is known as the group delay. For example, if I use this, let's say I have the group delay like this. Okay, and make it very simple, like make it the group, the phase delay is equals to minus omega. Make it very simple. In that case, the group delay is equals to d by dy. We have a minus and this minus omega, and which is equals to 1. So the group delay is 1, means what? So in practice, this is omega and this is the phase scale. So it is delayed with respect to the omega value. So let's say this is pi by 2 and this is pi and this is 0. If that is a linear one, it means that, what does it mean? You need to wait one sample to get back your original signal from the sender to the receiver. I'd like to discuss it here with this example. Let's say I have this filter HZ, we have designed that, and we are putting 3 signals here. And low frequency. And we are targeting, let's say we are targeting this point. So this 3 signal, how it actually been produced, let's say we have a signal xn, and inside xn, that is x1n plus x2n plus x3n. So we have 3 signals, and all 3 signals, this is your x1n, x2n, and x3n. Now, whenever they are passing through this filter, due to the phase response h omega, all the frequency component will not having their same phase. Whenever they reach to the output, they make some delay. So what kind of delay they make? We have already found that the group delay would be one sample. If that group delay is one sample for everyone, what you need to do? You need to just wait for one sample and then add everything. Whenever you got the first sample and you got the second sample, you need to make a delay. For example, this is it might be not from the signal processing. Let's say we have an image like this. Okay, I have the image like this, and now I am segregating this image in the 4 parts. I am sending it somewhere else. I am sending it somewhere else. I'm sending it somewhere else. I'm sending it. And after that, I need to reconstruct the image again. So this is number 1, this is number 2, this is number 3, and this is number 4. So in the first second, at the first second, I have sent the first one. So it actually been here. In the second second, we are having this. In the third second, we are putting this, and in this. So this is in 1, this is 2, this is 3, and this is 4. If we have some delay between each and every samples, definitely what we need to do, we need to wait how many seconds to reconstruct the signal back? How many seconds you need to wait to reconstruct your signal?
Four seconds.
You need to you need to wait 3 seconds to reconstruct your full signal. That means in the left side, in this case, if all the signals are passing through this and they made some delay, which signal made higher delay? According to the linear phase response, the group delay, if the group delay is constant, they are making same sort of delay. You can put same sort of delay for each and every signals, and you can get back your original signal with by knowing this group delay number. But if you have a nonlinear phase response, in that case, it's very difficult to understand when and which signal actually been penetrate through this filter, and you are originating your original signal by combining all the signals together. That makes a nonlinear relation between signal number 1, 2, and 3, and that's why your life become very difficult. I will talk about this more with some example, how this nonlinear phase response makes our life difficult, and how to solve that problem. So where the nonlinear phase actually been introduced? By IIR type filter. So how to tackle this problem? So there comes the all pass filter. It has an excellent characteristic by which we can control the nonlinear phase to the linear phase to some extent, not exactly for all conditions, but we can control that, the IIR filter nonlinearity to the linear filter. The fundamental thing is that if we have a different frequency component in a particular signal, in that case, if we have different phase delay, if we have a different phase response, nonlinear phase response with respect to each other, then after having the filtration, it's very difficult to reconstruct the original signal, to match these 3 frequency components together to retrieve the original signal back, and that makes some problem. Okay. So that is the end of today's lecture. So in the next day, we'll talk about the all pass filter and with some example why the nonlinearity makes our life difficult, and so on and so forth, inshallah. So thank you for your presence.